All right. So, quick reminder, we have a test next Tuesday. I'll have a test review out by this Friday, so you can at least study it through the weekend. Hopefully, that same day I'll be able to record the video for it too. The test shouldn't be as long as the last one because we're covering a lot less stuff, a lot less concepts to worry about. So it shouldn't be as bad, I hope. Or it could be lying. Who knows? Uh, anyway, let's go ahead and get started. We are starting 3.4. These are the three concepts you need to know. We're going to apply the rational zero theorem, apply the fundamental theorem of algebra, and apply Descartes' rule of sign. So go ahead and write those concepts down or take a picture, whatever you like, and then copy down these rational zero theorem. Again, this is kind of an overcomplication of what it is, but it's better to have it, not have it. And then we'll go over it in a second. But I will say this thing right here is probably the best summary of the rational zero theorem. Essentially, what the rational zero theorem says is that every single possible rational zero, so every single possible, I guess you can kind of think answer, is always going to be in this form right here, where it's always going to be a factor of the constant term all over a factor of the leading coefficient. That's pretty much what it factors down to. That pretty much every answer is pretty much going to be in that form. Or rational zero if you want like the fancy word for it. We good here? All right. So let's see what that actually looks like in practice now. We are going to list all the possible rational zeros. So my rational zeros in this case, remember, it's always going to be factors of the constant, which is the 15, over factors of the leading coefficient, which is 4. So the factors of 15, that's 1, 3, 5, and 15. Those are factors of 15. And factors of 4, that's just 1, 2, and 4. Okay? So all my possible rational zeros, they're going to be in the form of plus or minus the factors of 15, 1, 3, 5, and 15, all over factors of the leading coefficient, which is plus or minus 1, 2, and 4. So this is kind of how I like to kind of set it up before I write my final answer. So all my possible rational zeros will be plus or minus 1, 3, 5, 15, all over plus minus 1, 2, 4. And for my final answer, what I'm going to do is just put a plus minus and start mix and matching all these combinations. So it can be 1 over 1, which is a 1 over 2, which is a 1/2, 1 over 4, which is 1/4. Y'all see what I'm doing? I listed all my factors of the constant on top, all over factors of the leading coefficient of 4 on the bottom, and I'm just taking the first term of the first one and putting it over everything on the bottom. And then I'm going to go into the next one of 3 and do the same thing. So 3 over 1 is 3. That's another possible rational zero. Then 3 over 2 is 3 over 2. Then 3 over 4 is 3 over 4. And then we go into the next one, which is 5. So 5 over 1 is just 5. 5 over 2 is 5 over 2. And 5 over 4 is 5 over 4. Everyone with me? Any questions or anything? All right. And then we go on to the last number of 15. 15 over 1, which is 15. 15 over 2. And 15 over 4. So those are all my possible rational zeros. 1, 1/2, 1/4, 3, 3 over 2, 3 over 4, 5, 5 over 2, 5 over 4, 15, 15 over 2, and 15 over 4. So if I ever ask you what are all my possible rational zeros, this is how you do it. List out all the factors of the constant term, put it all over factors of the leading coefficient, and just mix and match those factors. Everyone have this written down or not yet? We good? Okay. Now I'm going to do something slightly different. Well, not really different, but we're going to add to it. Now what I want to do is I want to find the zeros. So the whole point of finding these rational zeros, what they are, they're just possibilities of what the solution is. So pretty much what I'm saying is that for this problem up here, if I told you, well, if this 4x cubed minus 13x squared minus 32x minus 15, if this equaled 0, these are pretty much your possibilities of where you start with. All right, these are possible answers. You start with these answers here. So when I tell you to find the zeros, that's pretty much what I'm saying here. I'm saying, well, figure out all your possible rational zeros, and that's what you're going to use to figure out, which of those are actually your zeros or not. So we're going to start by listing out all my possible rational zeros. So you have plus or minus factors of 3, which is just 1 and 3. All over factors of 2, which is plus or minus 1 and 2. So all my possible rational zeros are 1 over 1, which is 1. 1 over 2, which is 1/2. 3 over 1, which is 3. And 3 over 2, which is 3 over 2. Everyone with me? All right. So these are what I'm going to check to see, well, which of these are actually zeros or not. And what that means is that we're going to do synthetic division with these numbers right here. Okay? So we're going to start with 1. Start with the whole numbers. Don't deal with the fractions if you don't need to. Start with 1. So for 1, we start with 2. So remember the coefficients are 2, 1, -5, -1, and 3. And we do synthetic division like we did last class. Bring down the first term, that's 2. 1 times 2 is 2. Add going down is 3. 1 times 3 is 3. -5 plus 3 is -2. 1 times -2 is -2. Add going down is -3. 1 times -3 is -3. And you get a remainder of 0. So remember from the last class, something is a factor or something is a 0 if you have a remainder of 0. So because there's a remainder of 0, that tells me that 1 is a factor of this coefficient. So what that means is that this 2x to the 4th plus x to the 3rd minus 5x squared minus x plus 3, if I was to factor this like we did last class, this 1 tells me we have an x minus 1 as a factor. And from here we have 2x cubed plus 3x squared minus 2x minus 3. You remember from last class, if you divide something, you have a remainder of 0. That means you can factor it. So factors, finding the zeros, solving, all those are pretty much the same thing. They're doing the same thing, kind of slightly different wording, slightly different ways. So from here, I still have 2x cubed plus 3x squared minus 2x minus 3. I can't really factor this any way right now. So what I'm going to do is I'm going to do synthetic division again. The point of synthetic division is you want to do it if you don't really have any other option. Okay? Well, in this case, you could do factor by grouping, but I want to do synthetic division. So what you're going to do is you're going to start where you left off. So the one worked before, so there's a chance it could work again. So you start with what worked before and list out your new coefficients. So it's the one right here. The 2, the 3, the -2, and the -3. Everyone with me, guys? Any questions about what I'm doing or why I'm doing something? All right. And we're just going to do synthetic division again. This 2 goes down. 1 times 2 is 2. Add going down is 5. 1 times 5 is 5. Add going down is 3. 1 times 3 is 3. Add going down is 0.
I'm sorry.
Sure.
So why did we do it the second time?
So synthetic division, when you're trying to factor or solve it, you usually synthetic division is kind of like a last resort kind of thing. If you can't solve it normally, like we learned before, or you can't factor it, that means you don't really have an option. You have to use this theorem right here. This theorem exists because it's like, well, if you don't have any other option, this is going to work, right? So in this case, you see from the very beginning, the 2x to the 4th plus x cubed minus 5x squared minus x plus 3. You can't use the quadratic formula here, right, or complete the square or anything like we learned before because it's not a quadratic. It's to the 4th power, not the 2nd, right? So because of that, we use this theorem.
And we're trying to solve for x.
We're really trying to solve for its factors. We're trying to factor it all the way down, which is kind of the same thing. So we're trying to factor it. It's probably maybe that's like the best word to use. We're trying to factor it. So because you can't factor this any other way right now, we don't have any other tools to factor it. We're factoring it this way with synthetic division.
Okay, so first we still factor, so we're going
You're gonna keep
to
it's
division.
yes. So it's more that you see when we did synthetic division once, we used one. I just kind of picked any number from this combination right here. I started with 1 because it's the easiest one, and it ended up working. So that tells me this 1 is a factor with x minus 1. And this quotient, the 2, 3, -2, -3 in the bottom, that's another polynomial. Right? You fine with that?
Okay, so which is x minus because we took the one at the opposite.
Perfect.
And then the second parentheses is our quotient.
Yes.
Mhm.
We're going to do it again because, I mean, you could factor by grouping here, but I want to show you all synthetic division again. So right here, let's pretend we can't factor it any other way. So in this case right here, because we're going to say we can't factor it, we're going to do synthetic division again to break it down even more to get to a form that we can do. You usually don't do synthetic division unless you absolutely have to. So in this case, we're doing synthetic division to keep breaking it down. Yeah, because it worked before, so there's a chance it could work again. We don't know. So you're going to try it, and if it doesn't work, you go on to the next number. And in this case, it did work again, right? So what that means is that you take the x minus 1 from before. That didn't go anywhere. I didn't mess with it. That stays here. And then you have the new x minus 1 that we just got. And we have our quotient of 2x squared plus 5x plus 3. Does that make sense? Like, do you get how we got the x minus 1 times 2x cubed part? Oh, so do you know where the 2x cubed comes from? Yeah, right here. Right. So it's this, what you divided by times what you got is the same thing as the original. Right? It's like if you have 12 divided by 4, that's 3, right? That's like saying, well, 4 times 3 is 12. What you divided by times what you got, oh, it's not 0, it's 12, is what you originally had. That's the logic we're doing with polynomials. We're just saying, look, well, we had this really complicated one of 2x to the 4th plus x cubed minus 5x squared minus x plus 3. I divided by x minus 1 and got a remainder of 0. So what you divided by times what you got is the same thing as the original. So x minus 1 times this 2x cubed thing is the same thing as the original. But this can still factor down. So I'm gonna divide just this second parentheses And what we do when you divide it by x minus 1 is you get 2x squared plus 5x plus 3. So that 2x cubed plus 3x squared minus 2x minus 3, this is what breaks down to these two parentheses. Yeah, because we only divide that second parentheses, so that the original x minus 1 goes down. We have a new x minus 1 by what we just divided by, and a 2x squared plus 5x plus 3 from the quotient. All right. And now 2x squared plus 5x plus 3, you can do synthetic division again if you want to, but once you get to this part, it's a lot easier to just factor by hand, right? So in this case, I want factors of 6 that add up to 5. And that's just 3 and 2. And just divide these by 2. Right, so just going to rewrite it right here. I have 3 and 2. So we have 3 over my leading coefficient of 2, and 2 over my leading coefficient of 2. Well, 3 over 2 doesn't reduce, but 2 over 2 does, so just 1 over 1. So what that means is that 2x squared plus 5x plus 3, that's going to factor to 2x plus 3 and x plus 1. And we have x minus 1 and x minus 1 from before. And that's your factored form. Are we fine up to here, guys? Any questions about what I'm doing or why I'm doing something? So that's your, go ahead. Like from the beginning, you can choose anyone you want. And you'll see here, when I write out the answer, you'll see that every single one is actually in this list right here. If it's a real answer, they'll be in this list. You'll see right now. But you can start with any one you want. So I started with 1 just because that's the easiest. It depends. These are possible. These are possible solutions. We're not saying these are all the solutions. We're saying if you have solutions, if you have real solutions, it's going to be in this list right here. That's what it's saying. So basically what I'm saying, or what the problem is saying, is that you have a list of numbers here, and when you're dividing, you start with this list right here. That's what it's saying. Okay. Can I answer your question? Like, what's the question exactly? Yeah, you just pick one number, start with that, start with it like this. But there is a chance where the number you pick doesn't work. And if it doesn't work, like let's say I got a remainder of 1 or 2 instead of 0, like anything but 0, that means that number doesn't work. You move on to the next one. So like let's say in this case I did 1 and I got a remainder of like 2. Well, 2 is not 0, so you cross out 1, then you go to -1. And let's say -1 didn't work, so you cross out -1 and go on to 1/2. You get what I'm saying? So you kind of go on to, you kind of go down the list until you find one that works for you. Make sense now? All right. So x minus 1, 2x plus 3, and x plus 1. From here, you want to list out your zeros from these factors. So this x, the first x minus 1 tells me I have an answer of x equals 1. This second x minus 1 tells me I have another factor of 1. So that x minus 1 happens twice. That means I have a multiplicity of 2. You remember that word from last time? Multiplicity just means how many times does it happen. So x equals 1 with a multiplicity of 2. 2x plus 3 tells me we have a solution of -3/2. Right? If you have 2x plus 3, you set it equal to 0 and solve it. So subtract the 3 and divide by 2. And you get that x is -3/2. Are you fine with that? And then x plus 1 tells me I have a solution of x equals -1. And these are my answers. And if you go back to your original list, you'll see that 1, -1, and -3/2 were all on that list. And that's because anytime you have a real solution, it's going to be on the list of those possible rational zeros. Any questions about that, guys, before we keep going? Are we good? All right, let's keep going. Now we're going to do the same, find the zeros and their multiplicities. So I guess we kind of did the multiplicities before. We'll do the same thing, but we're also going to find their multiplicities. So remember, we start with all your possible rational zeros because x cubed minus 2x squared minus 14x minus 5. You can't really factor that by hand. So you want to know kind of what should I divide it by, what should I start with? And you start with your rational zeros. That's factors of 5 over 1. So factors of just 1 and 5 over factors of 1, which is just plus or minus 1 or 5. So my possible rational zeros are 1 and 5. So what I'm going to do now is I'm going to do synthetic division with these numbers. So I'm going to start with 1 because it's the easiest one to do. Just start with 1. My coefficients are 1, negative 2, negative 14, and negative 5. And we're going to do synthetic division with this. Bring down the 1. 1 times 1 is 1. Add going down is negative 1. 1 times negative 1 is negative 1. Add going down is negative 15. 1 times negative 15 is negative 15. And my remainder is negative 20. And that's not 0, right? So because it's not 0, that means 1 is not going to work. You go on to the next number. Me personally, I like to go positive to negative, so I'll do 1, then I'll try negative 1. So if 1 doesn't work, let's try negative 1. It's the same coefficients as before. So 1, negative 2, negative 14, negative 5. Bring down the first number. Negative 1 times 1 is negative 1. Add going down is negative 3. Negative 1 times negative 3 is a positive 3. Add going down is negative 11. Negative 1 times negative 11 is positive 11, and that is 6. And that's also not 0. So in this case, negative 1 is also not going to work. So we go on to 5. And 1, negative 2, negative 14, negative 5, same coefficients. Bring down the 1. 5 times 1 is 5. Add going down is 3. 5 times 3 is 15. Add going down is 1. 5 times 1 is 5. Add going down is 0. Finally got it. We got a remainder of 0. So what that means is that x minus 5 is a solution. And we have x squared plus 3x plus 1. Okay? So x squared plus 3x plus 1, this does not factor, right? There's no factors of 1 to add up to 3. What that means is that x squared plus 3x plus 1, the zeros or the solutions it's going to give me are not going to be rational numbers. So you have to solve it a different way. To find the zeros out of that one, you have to do it a little differently. You either have to do a synthetic division, or not synthetic division, sorry. You have to do the quadratic formula or complete the square. It's up to you. I'm going to do the quadratic formula. So to find the zeros of x squared plus 3x plus 1, I'm going to use the quadratic formula. So you have negative 3 plus or minus the square root of 3 squared minus 4 times 1 times 1 all over 2. Is everyone with me? Any questions about what I'm doing or why I'm doing something? All right, so you have negative 3 plus or minus the square root. That's 9 minus 4 all over 2. or negative 3 plus or minus square root of 5 over 2. Any questions? All right. So what that means is that this x squared plus 3x plus 1 from the very beginning, the zeros that it gives me is negative 3 plus or minus root 5 over 2. And then the x minus 5 tells me, well, you also have solutions of x equals 5. And those are my three zeros here. Make sense? Go ahead. Go up. To what part? This? Remember, this whole file is also located online, by the way. We're good? All right. Any other questions, guys, before we keep going? No? All right. And now we are going to find the zeros again for this problem right here. So x to the fourth minus 2x squared minus 3. Honestly, I think you can actually factor this if you want to, but we're not going to. We're going to do synthetic division. So in this one, I want plus or minus factors of the constant, which is 3. So 1 and 3 over plus or minus the constant of the leading coefficient of 1. So you have plus or minus 1 over 1, which is 1, and 3 over 1, which is 3. Everyone with me? So these are my possible rational zeros, and that's what I'm going to start with my synthetic division. So I'm going to start with 1. I like to start with 1 because it's an easy number to start with. And as a teacher, I can say that typically we're not going to make you do 7 of these to get to the right answer. Typically it'll be the first 2 or 3 that's going to work. First, like 1 to 3 that's going to work. It's unnecessary to make you do 7 of these to get the right answer. Anyway, start at 1. My leading coefficient is 1. Then we have a 0. Remember, you have to put in your placeholders. I'm missing an x cubed. So you have to put a 0 here. Negative 2 for the negative 2x squared. Another 0 for the x. Then minus 3. When it comes to synthetic division, you cannot forget those zeros. If you do, you're not going to get the right answer. So start with 1 and bring down 1. 1 times 1 is 1. Add going down is 1. 1 times 1 is still 1. Negative 2 plus 1 is negative 1. 1 times 1 is negative 1. Add going down is negative 1. And we can see this is not going to work because the remainder is not 0. Is everyone with me? Are we good? All right. Now let's go on to negative 1. 1, 0, negative 2, 0, and negative 3. Bring down that first term of 1. Negative 1 times 1 is negative 1. Add going down is negative 1. Negative 1 times negative 1 is still 1. Add going down is negative 1. Negative 1 times negative 1 is 1. And we can kind of see it's the same thing. We're not getting anywhere. So 1 and negative 1 don't work. We're going to go on to 3. So we're going to try 3 now with coefficients of 1, 0, negative 2, 0, and negative 3. Bring down the 1. 3 times 1 is 3. Add going down is 3. 3 times 3 is 9. Add going down is 7. That's 21. And we can see that's also not going to work. All right. Am I copying this down wrong? 1, -2, -3. Okay. Now we're going to try -3. And we have 1, 0, -2, 0, -3. Bring down the 1. -3 times 1 is -3. That's -3. -3 times 9 is 9. That gives you 7, -21. And this also is not getting us anywhere. So none of them work. What that means is you have no rational zeros. That means your answers are going to be complex or just radicals, not nice fractions or whole numbers. And that can happen. That just means you have to solve this some other way. In this case, this does factor, and I think root 3 is we're not going to do that. But we're not going to solve it that way. That's not the point of this lesson. But I just want to show you that this could happen. I won't do this on a test or quiz, but it was on the notes. You could see it on the homework. Also, make sure y'all see this. Does that make sense, guys? So it is possible so that your rational zeros aren't answers, and that your answers will be something like we had before, like this -3 plus or minus root 5 over 2. You could have something like this where it's a square root as an answer, or you could have some imaginary numbers, which could also be answers. Does that make sense, guys? Any questions about that? Okay, let's keep going. Now let's talk about the fundamental theorem of algebra. Probably two things at once. All right. So this is the exact wording you need to have down. This is what the fundamental theorem of algebra says. If f of x is a polynomial of degree n is greater than or equal to 1 with complex coefficients, then f of x has at least one complex 0. Essentially what this is saying is that if your coefficients are complex, remember complex numbers are like 1, 1 plus I, 2, 2 plus I, pretty much any number you know, then you will have a 0, you will have a solution. You can always solve for something. That's essentially what it's saying. That if you have a polynomial of a degree of 1 or greater, there is a solution to your problem as long as the coefficients are complex, which that's really all you're going to see in this class. And then underneath it, you have the linear factorization theorem. Um, that's really overcomplicated. Have it down so you can have it, but we're going to do a problem where I'm going to show you what it really means. This is supposed to say A is not equal to 0 right there. A of n does not equal 0. Are we good to keep going, guys? Is anyone still copying? Okay. Are we good? Anyone still copying? All, all, right. All 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 right. So this is pretty much what the linear factorization theorem is saying. If I'm telling you to find a polynomial p of x of degree 3 with zeros 2i and 4, uh, first of all, we're actually missing something. We didn't. Well, something they should have said, but they didn't, is that complex numbers is something called a complex conjugate theorem. You do need to write this part down. So the complex conjugate theorem, what that says is that essentially what it's saying is that if you have some kind of complex number as a zero, like let's say you have a zero of, I don't know, 1 plus I. If I'm telling you this is a zero, well, that tells you 1 minus I also needs to be a zero. Complex numbers come in pairs. So if 1 plus I is a solution, 1 minus I is a solution. If 2i is a solution, negative 2i is a solution. And this actually does go into square roots too. So if the square root of 2 is a solution, negative square root of 2 is a solution. That's pretty much what this theorem is saying, is that they come in pairs. Pretty much anything with a square root comes in pairs, right? I is still technically the square root of negative 1. So if you have a square root, it comes in pairs. 1 plus I, 1 minus I. 2i, negative 2i. Root 2, negative root 2. So what that means, for example 6, because I'm telling you guys that 2i is a solution, well, that means negative 2i also needs to be a solution. Because it has to come in pairs. If you see an I or a square root, it has to have a pair of the opposite sign. So what this means is that we have, what the linear factorization thing is saying is that, well, if you know your zeros are 2i, negative 2i, and 4, well, the factored form of that is just going to be x minus 2i, x minus negative 2i, and x minus 4. Essentially what it's saying is that the factored form is just x minus your 0, x minus 2i, x minus negative 2i, x minus 4. That is your factored form of your polynomial. That's what the linear factorization theorem is saying. It's just that, well, every solution, or your factored form of a polynomial, sorry, is just x minus that solution, or x minus that 0. Does that make sense, guys? Any questions about that? All right. So I'm going to clean this up a little bit before I solve it. So p of x is x minus 2i. The double negative just becomes an x plus 2i, all times x minus 4. Yes. So that's the complex conjugate theorem that I was talking about before. So all this theorem is saying is that i's and square roots come in pairs. That's essentially what it boils down to. I's and square roots come in pairs. So if I told you that 2i is a solution, so I'm telling you, look, 2i is a solution to this problem. Well, then negative 2i also has to be a solution. They have to come in pairs together. And the reason why is because if you look at the quadratic formula, what's in front of that square root of the quadratic formula? The the plus or minus, yeah, the plus or minus, right? It's the plus or minus. That plus or minus is what makes it so that anything with a square root gets a pair. Remember, I is the square root of negative 1, right? So anything that has a square root comes in pairs because of that plus or minus in the quadratic formula, right? So like if you put whatever solution we have here into the quadratic formula, you'll get, oh, well, you have plus or minus 2i at the end because of that plus or minus. That's where it's coming from. That's why they come in pairs. Are you everyone with me, guys? Ready to keep going? All right. So what I'm gonna do now is I'm going to expand this all out, multiply it all out. So do it part by part. Don't try to do everything at once. You really can't anyway. But do x minus 1, x minus 2i, sorry, times x plus 2i. I'm just going to put this to the side and see what I get. So x minus 2i times x plus 2i. So take the first term and distribute it to the second parentheses. X times x is x squared. X times 2i is 2xi. Distribute the negative 2i. You get negative 2xi, then minus 4i squared. Right? X minus 2i times x plus 2i gives you x squared plus 2xi minus 2xi minus 4i squared. Well, those two terms in the middle, they cancel out, right? Positive 2xi minus 2xi is just 0 because they're the same thing, with just different signs. And I squared, remember, that's just negative 1. So what I have is x squared minus 4 times negative 1. That's what I have right now because I squared is negative 1. So we get I squared, oh, sorry, x squared plus 4. Any questions about how I got that? So that what that tells me is that x minus 2i times x plus 2i is just x squared plus 4. And I still need to multiply it with that x minus 4. From here, take that x squared and distribute it to the next term. So x squared times x is x cubed. X squared times negative 4 is negative 4x squared. Then take the 4 and distribute that as well. 4 times x is 4x. 4 times negative 4 is negative 16. And that's your answer. So p of x is x cubed minus 4x squared plus 4x minus 16. That is one polynomial that has those zeros. What that means is that if I was to do synthetic division with this and factor it all the way down like we did before in the beginning of class, my solutions would be plus or minus 2i and 4. Make sense, guys? Any questions about that problem before I keep going?
What was the last thing you said about the two?
So what I was saying is that this polynomial that I got at the very end, if I was to, let's say I didn't give you the original problem, I just gave you this p of x right here, and I told you give me the zeros of this polynomial, and you did synthetic division like we did in the beginning of class, what you'd find is that your answers, your solution, your zero, sorry, would be 2i, negative 2i, and 4. That's what we did. Ready to keep going, guys? All right, let's keep going. Descartes' rule of signs. So copy this all down, and then I'll explain it. But essentially, what we're doing, well, actually, write it down first, and I'll explain it. So writing it down, guys. All right. And y'all have the test in the other class today, right? Thursday? I think it's supposed to be today, though. Still written down, guys? Still writing it down? Still there? Okay. Ready? All right. So essentially, what Descartes' rule of sign is saying is that the number of positive real zeros that you're going to have depends on how many times the sign is going to change. And I'll go over an example of what that means in a second. But basically, you just count, well, how many times you go from positive to negative coefficients or negative to positive coefficients throughout the normal equation. That's how many positive real zeros you can have. And you can have up to that many. And then you can always decrease by really just by twos. All right. And when it comes to the number of negative real zeros, what you start with is the amount of sign changes you have on f of negative x. Okay? I do think it's a little confusing to go in just words, that definitions. If we go through an example, it'll make a little more sense. So now we're going to go over this example to figure out how many solutions we have, or how many possible positive real zeros we have, negative real zeros, and imaginary zeros. All right. So we have f of x equals x to the fifth minus x to the fourth minus 14x cubed plus 32x squared minus 170x, 176. It's supposed to be 176x, I believe. So 176x plus 320. All right. Minus 176x plus 320. You all see what it's supposed to be, or is that kind of hard to read?
176x plus 320.
Yes. All right. So, to figure out the number of possible positive real zeros, what you want to do is go to your problem, your equation, and see, well, how many times do I switch signs? I started with a positive x to the fifth, then I switched to a negative x to the fifth. That's one change. And then I stay negative, then I have a negative right here, then I became a positive. That's two changes. Well, then add a positive, then I became a negative. That's three changes. And then you have a negative that became positive 320. That's a total of 4 sign changes for the original equation. Does that make sense, guys? You see how many times the sign of the coefficient change when it's ordered from highest degree to lowest degree. And in this case, it changed 4 times. That means the number of possible positive real zeros starts at 4. And when it's said in the definition, like it decreases by an even integer or something like that, all that means is that you can keep subtracting 2 to get all the possible numbers you can have. So you have 4, or 2, or 0. And obviously, you cannot have a negative amount of anything, so you don't go into the negatives, you stop at 0. So that means for this polynomial, you can have 4 real zeros, or 2 real zeros, or just 0. Positive real 4 positive real zeros, 2 positive real zeros, or no positive real zeros. Sorry. Does that make sense, guys? We're fine with how we got 4, 2, and 0. All right. Sorry? What about them? You count it. Oh, so what you do, so see in the definition, it says here, you can have less than a number of sign changes by a positive even integer. You see that? That means the 4, the amount of sign changes, that's just the maximum you can have. But you can always decrease it by 2. So it's this positive even integer. I think it's just easier to kind of think it's decrease. You can decrease it by 2. So you have 4, or 4 minus 2, which is 2, or 2 minus 2, which is 0. Yes. So all the possible ones decrease by 2. Make sense, guys? All right. Now for the number of possible negative real zeros, that's f of negative x. And getting f of negative x is actually pretty easy as long as you remember the only difference between f of negative x and f of x is going to be you change the sign in front of the odd exponents. So you had a positive x to the 5th. Well, now you have a negative x to the 5th because 5 is odd. You have a negative x to the 4th. Well, that's even. It's going to stay negative x to the 4th. You had a negative 14x cubed. Well, 3 is odd. It changes sign to a positive 14x cubed.
The second one for x4
Yes.
is it negative.
Well, it's because when you plug it in, you have negative x to the 4th power. Any number raised to an even power is always positive. So that's why all we're doing here for f of negative x is find all your odd degree exponents. So the 5, the 3x cubed, the x, and change those signs. That's all you need to do because only odd power exponents will have their signs change. Or you could plug it in if you want to, but you're just going to end up doing the same thing I'm doing right here. But it's the same thing. Does that kind of make sense what I'm saying? Everyone else, are you okay? All right, so after 14x cubed is a 32x squared. Well, x squared is positive. It's a 2 for the power. So it doesn't change signs. Then negative 176x, that's x to the 1st power. It's odd. It becomes a positive 176. Oh, 176x, sorry. And then plus 320. It's because when you plug in a negative, like let's say you plug in a negative into that x squared, you have 32 negative x squared. What's negative x to the 2nd power? Positive x squared. Yeah. That's why you only change signs in front of the odd powers. The odd powers because a negative number to an odd power is always negative, but a negative number, to an even power is always positive. Or if you want, just plug it in, you will get the same thing. But this little rule just kind of saves you a little time if you memorize it. Ready to keep going? Once you have f of negative x, we do the same thing. count the number of sign changes. So we start with a negative, and you stay a negative, and then you became a positive, and you never change from being a positive. That means the number of negative real zeros is 1. Oh, this should be blue. But it's going to be 1. And this has the same rule of saying you can subtract 2 to get your next number of negative real zeros. But the problem with this is that if you do 1 minus 2, you have negative 1, right? You cannot have a negative amount of anything. This doesn't really make sense. So that means you can never change from 1. It's always you're guaranteed, to have a negative real zero. So these are always going to stay 1. Because if you try to subtract 2 from 1, you get a negative number, and you can't have a negative amount of real zeros. It doesn't make sense, so that's why it just stays 1. Make sense? All right. So that's how you get to 2 real zeros. And now to get the number of imaginary zeros, that one's actually probably the easiest. Your total amount of zeros, or your total multiplicity, has to equal the degree of the function. The degree of the function is 5. So your total, including multiplicities, has to be 5. Does that make sense why it's 5, guys? Your total number of zeros is always going to match the highest degree exponent you have. In this case, it's 5. And then to find your number of imaginary zeros, you just kind of have to add up the columns and see, well, how do they add up to 5? Well, 4 plus 1 is 5, so that means the number of imaginary zeros you can have is 0. 2 plus 1 is 3. Well, 3 plus 5 is just, well, sorry, if you have 3 here, you can have 2 more. And same thing here is 4. And you can see that the number of real zeros, or imaginary zeros, also increases by 2. And that's how it goes, because they come in pairs. Does that make sense, guys? Any questions before we keep going on? Because I think that's the last example for 3.4 before we go on to 3.5.
What is the most common mistake for students in this subject?
This type of problem?
Not for this subject. We're talking about this Descartes.
Descartes? Well, the Descartes is only this type of problem. The biggest one is probably finding f of negative x. The blue part. They mess up the sign changes, is what I would say. It's probably the biggest mistake.
So I don't understand how do you know for
So when you try to find the number of negative real zeros, you find f of negative x, and you see how many sign changes do you have here.
Okay.
So you have negative, negative, that didn't change. Negative to positive, that is a change, right?
Okay.
And then you have positive, positive doesn't change. Positive, positive doesn't change. Positive, positive also doesn't change, right?
Yes.
So you only had one sign change.
Okay.
So that means you only have one possible negative real zero, or well, one possible negative real zero, yes,
Yes.
right? And from there, you can only increase and decrease by even numbers, so really by 2, right? So you have 1. Well, you can't really add from here. This is the maximum number you can have, but you can subtract by 2. Well, what is 1 minus 2?
1 minus 2.
Negative 1.
Sorry.
Negative 1, right? It's negative 1, and you can't really have a negative amount of zeros, right?
Yes.
Yeah, a polynomial can't say, oh, I owe you a 0. It doesn't make any sense. So that's why you can't have negative, and that's why this one's always stuck at 1, because you just can't change from it. You can't go from it.
Okay.
Does that make sense? Make more sense?
Yes.
Cool. Everyone else, are we okay? All right. Let's keep going. That's it for 3.4. We're going on to 3.5. So, apply notation describing infinite behavior of a function. Identify vertical and horizontal asymptotes. These are the concepts. Write these down, take a picture of them, come back to it later, whatever you want. But this is what you need to know. This is what I'm going to be testing on your test and what they're going to be testing on your final.
We're gonna be able to class notes later.
This stuff right here?
Yeah.
Yeah, this whole OneNote is it's linked to Canvas. So you can go on Canvas, you can find this there. So you can kind of go through the notes if you need to. And like always, if you have questions, just email me. I'm pretty quick to respond. Or office hours, whatever y'all need. Okay. Ready to keep going, guys? All right. Let's keep going. This is the definition of a rational function. Essentially, what a rational function is just a polynomial over another polynomial. That's all it is. Oh, where q of x. I don't know. The notes keep doing this, but q of x does not equal 0. Basically, you cannot divide by 0. So if p of x and q of x are polynomials, your rational function is where you have p of x divided by q of x, where q of x is not 0. We're fine with this, guys? Ready to keep going? All right. This is the behavior of rational functions. This might be a little confusing now, but we'll go over it in a bit, what it really means. But you just have it written down for now, for have it in your notes. Or take a picture of it, whatever you want. It's also online on Canvas if you just want to follow along. And we're about to go over an example of what this looks like. But this is kind of like the end behaviors we talked about, I think, 2 classes ago. But this is just pretty much notation. I guess the new thing will be these two right here. X goes to C plus. When you have an exponent as a plus or a minus, all that means is positive side, negative side, or right side, left side. We're fine here? Ready to keep going? All right. So example 1, we have a rational function. And we want to figure out, or we want to complete these statements. So the graph of f of x is given right here. And we're asked here, well, as x goes to infinity, f of x or your y's, where are they going? So as x goes to infinity, what we're saying is that as x keeps increasing forever, it goes to the right forever. Well, I can see my graph right here kind of just tails off towards this this dashed red line. That dashed red line is called a horizontal asymptote, and that's what determines your end behavior in this case, because it kind of breaks the function in a way. So in this case, well, as x goes to infinity, your f of x is going to that asymptote of 1. Right? If you see these dashed red lines, that means it's an asymptote. So these asymptotes you see as x as this blue line, that the blue line is the actual graph. As it's going to the right forever, it's getting closer and closer to this dashed red line. And that dashed red line is at 1. So as x goes to infinity, your y's are going to 1. Are you okay with that? Any questions here, guys? All right, and as x goes to negative infinity, to the left side forever, right? As x goes to negative infinity, as the graph is going to the left forever, your y's are also going to 1, because that's where the horizontal asymptote is. You can't, I don't want to say you can't cross it, but in this class, we're not going to cross it. So you see a horizontal dashed line, your end behaviors is going there. So in this case, it's also 1. Everyone with me? Any questions? All right. So now I'm saying, well, as x goes to 3 from the right side, right, 3 to the power of plus, that power of plus right there, that just means x goes to 3 from the right side. So as x goes to 3 from the right side, from this way here, I want to know, well, where your y is going. Well, you can see your y is just kind of going all the way up to positive infinity. Right? As the graph is going to 3 from the right side, this graph is just shooting straight up. You cannot cross a vertical asymptote, so you're going straight up to positive infinity.
Why?
Oh, because you're saying from the right side. See the power of plus right there, the 3 to the plus? That plus tells you from which direction. So the plus means from the right side. The negative means from the left side. So we're saying go to 3 from the right side. So from the right side, go to 3, you're going up to infinity. Right? Like if you're sitting right there, I can kind of approach you from the left or the right side, right? Well, the plus is telling you which side you're coming from. So if it's plus, I'm saying, well, I'm coming to you from the right side. If it's a negative, I'm coming to you from the left side, right? That kind of makes sense what I'm saying?
Yeah, so it'll always be like that.
From the right side.
Right.
Yes. Right to left, negative, left to right, because it's from the left side. So from the left side to 3, I'm going down to negative infinity. Make sense, guys? Any questions about that? Are we ready to keep going? Or is anyone still copying or have any questions?
Where's the starting?
Sorry?
Where's the starting? Blue line?
Sorry, say it again?
I'm just trying to figure out where's the line starting. Um, the blue line. Where it's starting at.
It's starts from the left side. You always grasp left to right. So start from the left side and going to the right, then it gets broken up by this vertical asymptote. Then you pick up again from up here and you kind of keep going this way.
I'm just thinking, is
No, it starts at negative infinity,
Negative infinity is
positive infinity. Well, it stops at 3, and then it picks up again right after 3 and keeps going to positive infinity. Sorry?
What is the unit of x minus 1 or x minus
What do you mean by it? I'm trying to understand the question so I can answer. What do you mean by it? What's the point of x minus 1?
1?
Why is it there? Well, it's because anything you put into a function is always gonna to change it. So the x minus 1 up there, it's it's kind of a hard question to answer because anything you put into a function is going to change it somehow. It's going to make it go up, down, left, right, completely change it completely if you throw in a variable. I mean, I guess I can show it on Desmos. So if you just have 1 divided by x minus 3 like this, your graph looks like this, right? If I was to make this to an x, what was it, x plus 1 or x minus 1? If you look at right here, if you just change it to x minus 1, it's going to change it some, right? It is going to change it. And that's kind of what it does. I'm not really sure if that answers your question or not.
Like in the paper, the graph will be there only that version.
Say it again?
The,
The test? Oh, in the test? Next class, we're actually going to learn how to graph these. And it's not as bad as it looks. It's pretty straightforward, honestly. But that's going to be next class's problem. But we will learn how to graph these. It's honestly not the worst thing. Okay. All right. Any other questions before we keep going? All right. Now we're going to figure out vertical asymptotes. So you all see how this vertical red line right there that's going up and down, that vertical dashed line, the red one, that's called a vertical asymptote, and it's there for a reason. So one of the biggest things you need to remember is you cannot divide by 0. All right? You cannot divide by 0. You need to keep that in mind when you're doing anything. And that's pretty much the whole point of vertical asymptotes. This is, I guess, the formal definition of it, but it's pretty complicated for what it is. Essentially, a vertical asymptote, all it is anything that makes the denominator 0 is going to be a vertical asymptote. Sorry. So copy this down, then I'll go back to the previous problem and show you that vertical asymptote. Because there's a reason of why it's where it is. All right, there's a reason it's at that x equals 3 part, and that's because that is what makes the denominator 0. Again, I don't really like this definition of vertical asymptote. I don't think we're going to get into of how to figure out which way is going to go up or down. But what you need to know now is a vertical asymptote happens when you divide by 0. If you go back to the previous problem, you see how here you have x minus 3 on the bottom? Well, if x equals 3, you divide by 0, right? That's why there's an asymptote at x equals 3. A vertical asymptote at 3, because you cannot equal 3, and that breaks up the whole function. That's what dividing by 0 does. It kind of messes everything up. It distorts it and breaks it up. That's why when x is 3, it makes the graph look completely different, and that's what happens. Any questions about that before we keep going? Sure. So you see here we're dividing by x minus 3, right?
Yes.
I'm not sure what's wrong with that. So the reason why we have a vertical asymptote x equals 3 is because anything that makes you divide by 0 breaks the function and makes it weird. It gives it a vertical asymptote. So you see here how there's this red vertical line right here. Well, it's not a coincidence. It's at x equals 3. That's because if you plug in an x is 3 here, you have 3 minus 1 over 3 minus 3, or 2 divided by 0. Remember, you cannot divide by 0, right? That's why when x is 3, like this is when x equals 3, you get 2 divided by 0. Well, that can't happen. That breaks the whole function. That's why you have an asymptote there.
So
It's
when
what
you solve for 0, that gives you.
your asymptotes. Yes, the zeros are the bottom, not the top, but just the bottom. And I think that's pretty much what this slide right here is going to say too. This one is pretty much going to say the same thing I just said. That vertical asymptotes happen when you divide by 0. So what you do when you have a rational function, look at the denominator. Any x value that makes the denominator 0 will be a vertical asymptote. Any questions here, guys? Are we okay?
So that, oh, that's the verb. Okay.
Yeah, vertical. We're going to do horizontal in a bit. So we're going to find some vertical asymptotes. So in this rational function, I have x minus 3 all divided by x squared minus 4x minus 5. So to figure out the vertical asymptotes, that's what's happening at the bottom. So I'm going to factor this out. So the top doesn't factor, that stays x minus 3. But the bottom is going to factor to x minus 4. Or not x minus 4, sorry, x minus 5, x plus 1. So the bottom factors to x minus 5 times x plus 1. So what that means is that x minus 5 and that x plus 1, those are your vertical asymptotes. So your vertical asymptotes are x equals 5 and x equals negative 1. Your vertical asymptotes will be whatever makes the denominator equal to 0. In this case, if you plugged in a 5, you have 2 over 0. If you plugged in a negative 1, you'd have negative 4 over 0. So anything that makes you divide by 0 will be an asymptote, and you get that by factoring the denominator, and each factor, each 0 of the denominator is your asymptotes. Right? X squared minus 4x minus 5 factors to x minus 5 times x plus 1. Well, that tells me that x equals 5 is a 0, and x equals negative 1 is another 0, or not 0, sorry, vertical asymptote. So x equals 5 and x equals negative 1 are your vertical asymptotes. Are we fine with that? Any questions, comments, concerns? No? All right. So now, for this example, I want to figure out what values is the function undefined, write the domain of f in interval notation, and identify the vertical asymptotes. So, for this one here, just factor it out like normal. So before you do anything with rational functions, you always want it factored. So I'm going to factor this in the bottom. We have 3 times x minus 2 all over the bottom factors to x minus 2 and x plus 1. Right, the top has a GCF of 3. You can factor out a 3 to get 3 times x minus 2 all over x minus 2 times x plus 1. And that's your factored form. And that's what I'm going to work with. Okay? So now let's go to A. A is asking me for what values is the function undefined. You're only undefined when you divide by 0. That is the only time you'll ever be undefined, is when you divide by 0. So in this case, well, that'll be 2 and negative 1. So I'm undefined at 2 and negative 1. For B, if I write my domain in interval form, your domain will be everything but where you're undefined, which is 2 and negative 1. So that means to write your interval notation, you start from negative infinity. You go to the smaller of the two, which is negative 1. Then it's negative 1 to 2. Then 2 to infinity. Essentially, if you want to think about it this way, in a number line, we have negative 1 and 2. My domain is everything but those two numbers. Are we okay with that? The domain is everything but those two numbers. That's what makes it undefined. So that means on a number line, my domain is going to be all of this, not including the 0. That's going to be empty. All of this, not including 2. Then the rest of it. Does that make sense, guys? Your domain will be everything but those two numbers. So in a number line, this is what it's going to look like. It's going to be shaded everywhere but these two. So if you want to write this in interval notation, well, it starts at negative infinity all the way to negative 1, but not including that. Then negative 1 to 2, not including the 2. Then 2 to infinity, and that's it. Make sense, guys? Any questions or anything? Okay, let's keep going. Now C, identify the vertical asymptotes, if any. So I'm going to rewrite the equation. X minus 2 all over x minus 2 times x plus 1. Or 3 times x minus 2, sorry. Right, that's my equation, right? And we said vertical asymptotes is anything that makes the denominator equal 0, right? So there's a little caveat to that. I will say for me, you will not need to know this for the test, but I'm going to say it anyway. And I don't think that's on the final either. Yeah, I don't see it on the final exam review either. So you don't really need to know this, but I'm going to say it so you understand it, maybe. This x minus 2 and this x minus 2 here, they cancel out. So what you have is 3 over x plus 1. So you're at your vertical asymptote, it's only x equals negative 1. At x equals 2, that's something else called a hole, but that is not something I'm going to test on. I don't see it anywhere on the review or the final exam review or in the concepts that they gave me. So you don't need to know about that. So, I mean, that's how you do it. But not something I would really stress about. Are we okay with that? Ready to keep going? Or any questions about this or anything we've talked about? No?
X equals.
The vertical asymptote.
Oh, okay. I thought you were doing.
No. Vertical asymptote. Are we good? Okay. Now horizontal asymptotes. Horizontal asymptotes are a little worse, but I think the hardest part of it we're not going to be going over, so it's not a big deal. All right, so horizontal asymptotes, they're the dashed lines that go horizontally, and what they do is they give you your end behaviors. Your horizontal asymptotes is tell you what's happening as x goes to positive or negative infinity. It's what shapes the graph as it goes to those extremes. Now, the important part of identifying your horizontal asymptotes. So these are the definitions. I don't like these definitions. I'm going to give you my own way to do it. So basically, what it's saying is that if you have some type of rational function, if the degree of the top is bigger than the bottom, you have no horizontal asymptote. If it's bigger on bottom, you have y equals 0. And if they're the same, you have a slant asymptote, which we are not going into in this class, so we don't even need to worry about that. All right. The degree of the top and degree of the bottom. So I really wouldn't write this part down, to be honest. But well, I will write because this is an easier way to go about it. So make sure we're not doing slant asymptotes first. Yep, we're not. Perfect. See. Perfect. Okay. So we don't have to worry about slant asymptotes. That makes life a lot easier for you guys. What I would memorize is this really dumb acronym called BOBO, Botan, eats DC. It's a very dumb acronym, but I learned it when I was in high school and it never left my mind. So it clearly works. And it does stand for something. In this acronym, we're talking about the degrees of the function. So when we have BOBO, that's saying bigger on bottom, your asymptote is 0. So bigger on bottom, that's supposed to be 0 here. Botan, bigger on top. You have none. East DC. Oh. Exponents are the same. Divide coefficients. So hopefully you can actually read this. Can you? Not really. Yes. Okay. It is a dumb acronym. So yeah, if I can find something better online. That actually has a nice picture up online. We're going to take this one. So this picture right here, if it saves nicely, pretty much says what I'm saying here, but probably in a nicer picture than I have. But essentially, bigger on bottom 0, bigger on top none. Exponents are the same. Divide coefficients. And we're going to go over some examples, but this is how I've always kind of kept it in mind, how I've always kind of remembered the rules. It's pretty nice. It's a dumb acronym, so it's really hard to forget. And it tells you how to get your horizontal asymptotes. And it's all talking about the degree of the function on top compared to the degree of the function on the bottom. Any questions here, guys? You have this written down or not yet? Yes. Anyone still copying? Need a few more seconds? A few more seconds? Okay. Good. Everyone else okay? All right. So let's go over some examples. So I want to figure out the horizontal asymptote of this function, if any. So remember, Bobo bot eats DC. We're going to see, well, what is the degree of the top compared to the bottom? So the degree of the top is 1. And the degree of the bottom is 2. Right? So the degree of 1 over degree of 2. So that means it's bigger on bottom 0 is Bobo. So y equals 0 is your horizontal asymptote. Right? Bobo bigger on bottom 0. So because your degree is bigger on bottom, your horizontal asymptote is 0. And it's always y equals.
When you say the
Degree?
degree, yeah, you mean the exponent?
Yes. So the biggest. Yeah, we'll say yes for that. So the biggest exponent is on bottom of 2. The degree of the bottom is 2. So it's bigger on bottom 0. So that's why it's y equals 0. Are you okay with that, guys? Any questions? Always y equals yes. Yes, exactly. Horizontal means y equals, vertical means x equals. Are we good? Anyone have a picture if they have one, if they need one? All right. All right. Now, for this one, determine the points where the graph of f crosses its horizontal asymptote. We are not going to do that. What we are going to do, though, is we're going to figure out the horizontal asymptote. That's what we care about anyway. So, in this case, its exponents are the same. So, it's not bigger on top or bigger on bottom. It's a power of 2 over a power of 2. That eats DC. What that means is exponents are the same, divide coefficients. So you want to divide the leading coefficients. The leading coefficient of the top is 2. The leading coefficient of the bottom is 1. So your horizontal asymptote is y equals 2 over 1. It's supposed to be a 1. Or just 2. And that is your horizontal asymptote. Make sense, guys? Any questions about that? Are you ready to keep going? All right. I guess I'll give you a quick other example. If we have something like f of x equals x to the 7 minus x to the 4th plus 13 all over x squared minus, or say plus 7. The horizontal asymptote here, the degree is bigger on top, right? Power of 7 over power of 2. So this would be a case of button bigger on top, none. So that means we have no horizontal asymptote. And that's kind of how you use Boba each DC. Just look at each degree on top and bottom, compare them, and put it into the acronym and see what you get. Make sense, guys? Any questions here? Comments, concerns? No? This one? I'm sorry? Oh, because the degree is bigger on bottom, right? So Bobo means bigger on bottom 0. So the degree is bigger on bottom, it's 0. Make sense? Everyone else, are we okay? All right. How long is 3.6? 4 examples. I mean, it's not terrible, but it's going to take more than 10 minutes. All right, that's it for today. Let me take attendance, and then y'all can